Hello everyone, welcome to Learn Wireless Technology. In this tutorial, we will discuss about the functions of PDCP layer. We will see the main functions of PDCP layer, the architecture of PDCP layer, and its various important procedures. We will also see the different PDU structures. So let's start. PDCP, as we know, is a sub-layer of layer 2 of LTE protocol stack. It sits at the top of layer 2 protocol stack above RLC layer. It interfaces the RRC layer for control plane data transfer and IP layer for user plane data transfer. Let's have a look at the functions provided by the PDCP layer. So, PDCP layer provides data transfer functions to help in transferring user plane and control plane data to and from the upper layers. It receives the SDUs from the upper layers and transfers them as PDCP PDUs to the lower layers. And in the other direction, it receives the PDUs from the lower layers and sends SDUs to the upper layers. PDCP is responsible for security functions. It performs ciphering and deciphering of user plane and control plane data. It also performs integrity protection and verification for control plane data. PDCP is responsible for performing header compression and decompression of IP data. It performs header compression services to improve the efficiency of over-the-air transmission. The header compression is based on robust header compression, that is ROHC protocol for user plane data. PDCP is also responsible for ensuring lossless data transfer during handover and radio link failure. It maintains the PDCP sequence number and offers services such as in-sequence delivery of upper layer PDUs and duplicate detection of lower layer SDUs when the re-establishment of lower layers takes place after handovers and radio link failures. During handover, the source eNode B buffers the unacknowledged packets and transfers them to target eNode B. The target eNode B forwards these packets to UE after successful handover, hence avoiding any loss of packets. It also retransmits any missing PDUs during re-establishment of PDCP after radio link failures. The transmitter maintains a buffer to store transmitted PDUs to support this functionality. PDCP also performs timer-based discard, where an SDU is discarded when the discard timer expires. It also discards any duplicate packets arrived. Now let's take a look at the architecture of PDCP layer. So this is one possible architecture of PDCP layer. It consists of multiple PDCP entities. There can be several PDCP entities defined for a UE, and each PDCP entity is configured to carry data for one radio bearer. So basically, each radio bearer, that is data radio bearer and signaling radio bearer, is associated with one PDCP entity. And each PDCP entity is associated with one or two RLC entities, depending on the radio bearer characteristics, whether it is unidirectional or bidirectional, and the RLC mode used, that is unacknowledged or acknowledged mode. There is no association of PDCP entity with transparent RLC mode, hence no PDCP data goes through this mode. As we know, unacknowledged RLC mode has two entities each, one for transmitting side and one for receiving side. So in such case, the PDCP entity is associated with both the RLC entities, that is one for each direction. The PDCP layer is configured by upper layer, that is the RRC layer. Now, this diagram represents the processing blocks at the transmitter side. The processing blocks are shown in the order they are applied on PDCP SDUs for control plane and user plane data. Some of the blocks are applicable to user plane SDUs only, such as header compression, and some are applicable to control plane SDUs only, such as integrity protection. The sequence numbering block will add sequence number to each incoming data packet in order to ensure in-sequence delivery of PDUs. If you look at the control plane data processing blocks on the left hand side, The PDCP receives the control or signaling data from the upper layers, that is NAS and RRC layer, via SRB1 and SRB2 in the form of PDCP SDUs. Control PDCP SDUs are also generated in the PDCP layer itself. For example, the PDCP status PDU and ROHC feedback packet are generated in the PDCP layer itself. Now the SDUs are processed as it moves further through the blocks that follows. The SDUs are integrity protected and ciphering is applied. After that, the PDCP header is added to the SDU, which results in PDCP PDU. The PDUs are delivered to the RLC layer for transmission over the air. Now coming to the user plane data processing blocks on the right hand side, PDCP receives IP packets for transmission from upper application layer. The transport protocol may be TCP, UDP or RTP on top of IP protocol. Using the ROHC header compression technique, the header overhead appended to the data packet is reduced to great extent. The PDCP header is added to the SDU after that, and the resulting PDU formed is delivered to the RLC layer for transmission. So at the transmitter side, the data processing happens in the order from top to bottom according to this figure. Now the receiving side of PDCP entity has similar processing blocks, but the received PDU is processed in reverse order. That is, the data processing happens in the order from bottom to top according to this figure. At the receiver side, the PDCP header is removed from the PDCP PDU. For control plane, the deciphering of data takes place and integrity protection is checked. And for user plane data, deciphering and header decompression of PDCP SDUs is performed. The PDCP then performs in-order delivery check and duplicate detection of PDCP SDUs before delivering the PDCP SDUs to higher layers. Couple of things needs to be noted here. The security steps mentioned here are mandatory in LTE, but the header compression is optional. The retransmission buffer in user plane is applicable only when the PDCP entity is associated with acknowledged mode RLC entity. To support retransmission, the incoming data packets to be transmitted are stored in the retransmission buffer, and whenever there is any missing PDU or delivery failure at the receiver, the PDUs are retransmitted. Now let's look at some of the important PDCP procedures in more detail. Let's start with header compression and decompression. As mentioned earlier, the header compression protocol is based on ROHC, that is, Robust Header Compression Technique. It is an algorithm to compress the header of IP packets received from application and IP layer. The size of header of an IPv4 packet is usually 40 bytes, and an IPv6 packet has header size of 60 bytes. Now, this size cannot be considered significantly huge for the applications such as file transfer or browsing, as the 40 to 60 bytes of header won't contribute much to the overhead. But if we consider applications such as voice over IP or voice over LTE, where small chunks of data of size 30 bytes are carried that are generated very frequently, such header creates a large overhead as the header part takes more resource than original data, which is inefficient use of network resources. Hence, it is necessary to compress the data when such applications are used. Using ROHC technique, the header of size 40 to 60 bytes can be compressed to 1 or 2 bytes. Now, the principle of ROHC operation that provides such large degree of header compression is quite simple. So, any full-size header consists of many fields such as source and destination address, source and destination ports, etc., which helps to identify a packet. There's also a lot of other information stored in it and contain lot of redundancy as well. During a packet flow, some of the fields remains constant, such as source and destination address in IP header and source and destination ports in UDP TCP header. And some fields keep changing from packet to packet in specific pattern, such as the identifier field or the checksum field. So during initial transaction, few packets are sent with full size header without any compression. This is to establish the context between the compressor and decompressor sides. The context comprises information about static and dynamic fields and the changing pattern of the protocol headers of the dynamic fields. So once the context is established, the fields which remain constant throughout a session need not be sent for every transaction. For subsequent transactions, the header is sent only with those information which changes randomly after every transaction. So transmitting only the changing part of the header gives an effect of data compression. Hence, using ROHC is an effective way of reducing the header size greatly. This technique is robust against bit errors, packet loss, and long round-trip delay. So this is how the header compression principle works. Now, as seen in this example, the header contains 40 bytes that comprises 20 bytes from IP, 8 bytes from UDP, and 12 bytes from RTP, whereas the payload just contains 20 bytes of data. So the ROHC is used to compress the 40 bytes of header to as low as 2 bytes. Now there are different ROHC profiles defined which are used to compress packets with different types of protocol headers such as UDP, RTP, IP, TCP, and ESP. This table represents the supported header compression protocols and profiles. The ROHC profiles and parameters are signaled and configured by RRC layer. Now, this is a UE capability message sent by the RRC layer of UE. It informs the network about the ROHC profile it supports, for which the flag is set as true. In this case, the UE supports ROHC profile 1 and 2, where profile 1 indicates ROHC RTP, which is used for compressing packets with IP, UDP, RTP protocol headers, as can be seen from this table. And profile 2 indicates ROHC UDP, which is used for compressing packets with IP UDP protocol headers. Likewise, there is a complete list of profile identifiers, each representing a different usage of compressing packets with different protocol headers. There's one instance of ROHC for each PDCP entity. The next procedure is ciphering and deciphering. PDCP performs the ciphering and deciphering functions which applies to both control plane and user plane data. Ciphering is applicable to only the data part of the PDUs. It is not applicable to control PDUs. The data part can be an uncompressed or compressed PDCP SDU. The ciphering algorithm and the key to be used are configured by upper layers. In LTE, the algorithm used for ciphering and deciphering is EAA, that is EPS encryption algorithm. The parameters required by PDCP for ciphering are provided by the upper layers, and they are the inputs to the ciphering algorithm. Here's the list of inputs provided to the ciphering algorithm. Key. These are the ciphering keys for control plane and user plane. For control plane, the ciphering key used is KRRCENC, and for user plane, the ciphering key used is KUPENC. The length of the key is 128 bits. Bearer. It is the radio bearer identity. It is a 5 bits value derived from the value corresponding to information element RB identity, which is provided by the RRC layer. Direction. It gives the direction of the transmission. 0 indicates uplink direction and 1 indicates downlink direction. It is a 1-bit value. Count. It is a 32 bits length. It is the combination of HFN, that is hyperframe number, and PDCP sequence number. The length of the PDCP sequence number is configured by upper layer. For each radio bearer, a count value is maintained for each direction. Length. It is the length of the key stream block. So as you can see in this figure, All the parameters are given as input to the ciphering algorithm EAA. The resultant key stream is mixed with the input data, which generates a ciphered stream. Similarly, at the receiving end, deciphering takes place using the same key stream and the original data is extracted. So this is how the ciphering and deciphering works at PDCP layer. Ciphering process can also be disabled by applying EEA0 algorithm. Next procedure is the integrity protection and verification. PDCP performs the integrity protection and integrity verification for the PDCP entities associated with signaling radio bearers. The integrity protection is performed on the PDU header and the data part of the RRC and NAS signaling messages carried by signaling radio bearers before ciphering is done on them. The integrity protection algorithm and key to be used by the PDCP entity are configured and activated by upper layers, that is RRC. In LTE, the EIA algorithm, that is EPS integrity algorithm, is used for integrity protection. For integrity protection and verification, the parameters required by the PDCP as an input to the integrity protection algorithm are provided by the upper layers. The list of inputs provided to the integrity protection algorithm are similar to those provided to ciphering algorithm. Key. It is the integrity key KRRCINT which is provided by the upper layer. The length of the key is 128 bits. Bearer. It is the radio bearer identity. It is a 5 bits value derived from the value corresponding to information element RB identity which is provided by the RRC layer. Direction. It gives the direction of the transmission. 0 indicates uplink direction and 1 indicates downlink direction. It is a 1-bit value. Count. It is the combination of HFN and PDCP sequence number and it has a 32 bits length. And the signaling message which comprise of PDCP PDU header and data is also provided as input to the integrity protection algorithm. So this figure explains the integrity protection and verification operation. At the transmitter side, the signaling message is passed through the integrity protection algorithm. Using the integrity key along with the rest of the parameters as an input to the algorithm computes a 32-bit integrity field referred as MAC-I and appends this field to the message. At the receiver side, the integrity field is separated from the signaling message. The receiver calculates the XMAC integrity field based on the input parameters and compares it with the received integrity field MAC-I. If the calculated XMAC corresponds to the received MAC-I, then the integrity protection is verified successfully. Now let's look at the re-establishment procedure performed by PDCP. So PDCP performs re-establishment procedure after handovers or radio link failures occur. When the data radio bearers are mapped to the RLC layer, which is configured in acknowledged mode, the PDCP stores the SDUs in its retransmission buffer until the RLC acknowledges PDCP of the successful reception. So when PDCP re-establishment happens due to handover or radio link failure, there's a brief interruption in data transfer over the air which may lead to loss of packets. In such case, once the re-establishment is successful, the transmitter side shall resend all the PDCP SDUs stored in transmission buffer which are not yet acknowledged by RLC. Now, it may be possible that some of the SDUs might have already been sent by the transmitter before. So, in order to avoid transmission of SDUs twice, the receiver side shall send a status report after PDCP is re-established. The status report is applicable only for acknowledged mode user plane bearers. The report indicates the list of received and missing PDUs for retransmission. Now, in case the PDUs are received out of order at re-establishment, then PDCP shall perform reordering of the PDUs according to the sequence number. After PDCP re-establishment, the ROHC parameters will reset and the values of sequence number and HFN shall be continued. When the data radio bearers are mapped on RLC unacknowledged mode and PDCP re-establishment happens, the SDUs that have been assigned a sequence number but not yet transferred to RLC layer will now be transferred. The values of sequence number and HFN along with the ROHC parameters are reset. And in case of signaling radio bearers, all the messages will be discarded and the sequence number and HFN values will be reset when the PDCP re-establishment takes place. Now let's take a look at different PDU structures in PDCP layer. We will first see the PDCP structures for SRBs and DRBs. This is the PDCP data PDU structure that carries data for control plane signaling radio bearers. Signaling radio bearers, as we know, are used to carry signaling messages from RRC and NAS layer. The messages are carried on SRB1 and SRB2. The length of sequence number field is 5 bits for control plane SRBs. MAC-I field has 32-bit length and carries a message authentication code. It is attached at the end of PDCP control plane PDU and used for integrity protection. R is a 1-bit reserved field. This is the PDCP data PDU structure when a 12-bit sequence number length is used. This format is applicable for PDCP data PDUs carrying data from DRBs mapped on RLC acknowledged or unacknowledged mode. In the DC field, D indicates that the PDU contains user plane data and C indicates that it carries control plane information generated at PDCP layer. Now the DRB data PDU can have a short sequence number of length 7 bits. The sequence length is configured on per DRB basis. This is the PDCP data PDU structure when a 7-bit sequence number length is used. This format is applicable for PDCP data PDUs carrying data from DRBs mapped on RLC unacknowledged mode. Now let's see the structure of a control plane PDU. This is the format of PDCP control PDU carrying one interspersed ROHC feedback packet. It has a variable length. And this is the format of the PDCP control PDU carrying one PDCP status report. This format is applicable for DRBs mapped on RLC acknowledged mode. The FMS field indicates the PDCP sequence number of first missing PDCP PDU. The length of the sequence number can be 12 bits, 15 bits or 18 bits. Accordingly, the length of FMS field can also be of 12 bits, 15 bits or 18 bits. The bitmap field has variable length and it indicates whether or not a PDCP SDU is received. The bit when set to 0 indicates the PDU is missing, and when set to 1, it indicates the PDU is received and does not need retransmission. So this was all about the PDCP layer functions, the architecture and processing blocks, different PDCP procedures, and PDU structures. I hope you understood them all. Thanks for watching.